Hello and welcome to Algebra 2 Lesson 68. In this lesson, we're going to learn about inverse functions. So at some point in your Algebra 2 course, you're going to run into this topic known as inverse functions. And really, this is going to lay the groundwork for us. And we're going to start talking about exponential functions and logarithmic functions as soon as we conclude with inverse functions. So when we think about inverse functions, basically, we're thinking about functions that reverse each other. But before we kind of jump in and start talking about inverse functions, I want to just make sure that you understand the basics of a function. So we want to just do a quick review. At some point in either Algebra 1 or at the beginning of Algebra 2, you talked about functions, and we learned that a function was nothing more than a relation, or a set of ordered pairs, where each x value corresponds to exactly one y value. So there's a clear association with a function. I give you an x value, and you can tell me what the y value is that's associated with it. So as an example, let's say we look at this set of ordered pairs here, this relation, and we say, is this a function? So for each x value, is there a unique y value that's associated with it? In other words, is there a clear association? So to see this, let's kind of draw a typical picture that you'd see in this section. So let's set this up and say that this is the domain. This is the domain, or again, the set of allowable x values. So what exists in our domain here? Well, we just have a set of ordered pairs. So remember, the ordered pairs are x, comma, y. So the first component, or the first entry in each ordered pair, represents the x value. So we have an x value of 3, we have an x value of 2, we have an x value of 8, and then we have an x value of 6. So our domain consists of those four numbers. When we think about the range, that's the set of allowable y values. So in this case, our range consists of 7, 5, we have a 7 again, so I'm not going to double list that, and then 3. Now again, with a function, for every x, there's going to be a clear association with a y value. So if I ask you, what is y when x is 3? Well, when x is 3, y is 7. So there's a clear association there. When x is 2, y is 5. So when x is 2, y is 5. When x is 8, y is 7. So when x is 8, y is 7. And then when x is 6, y is 3. So when x is 6, y is 3. So this is a function because for every x value, there is a clear association with one and only one y value. Now, the common thing that comes up in this section is that, hey, well, I have a 7 here for y, and then I have a 7 here for y as well. And you'll see that I listed this up here. We said that a function is allowed to have y values that correspond to different x values. So we have that here. And that's allowed because, again, there's still a clear association. If I say, hey, x is 3, what's y? I know the answer is 7. If I say, hey, x is 8, what's y? I know the answer is 7. So it's okay that that occurs because I have a clear association. What I cannot have, let me kind of scroll back down. With a function, if I erase this and this, and let's say I change this up a little bit and I say, now I have the ordered pair 3, 5. So let's erase 2 from the domain. And let's say that 3 is now mapped to or linked with 7, but 3 is also linked up with 5. So the reason this violates the definition of a function is that x does not have a clear association with a y value. If I say, hey, if x is 3, what's y? You do not know whether to answer 7 or 5. Right? Y could now be 7 or it could be 5. So that's why we always say for each x value, there is one and only one y value. So there can be a y value that's associated with more than one x value, but there can't be an x value that's associated with or linked up to more than one y value. Now, we're going to introduce the concept of a one-to-one function. And you have to understand this to be able to get into this topic of inverse functions. So a one-to-one function, let me just highlight that, has a stricter definition. With a one-to-one function, we see that each x value corresponds to one y value. That's the same as before, okay? We've always had that rule. But now we're going to say each y value corresponds to one x value. All right, so when we have a one-to-one function, and we'll learn how to determine if we have one or not later on in the lesson, but assuming that you do have one, we can create a function known as the inverse, okay? The inverse, and this is by interchanging, so in other words, swapping x and y. So your x values become y values, your y values become x values. So we talk about the set of x values as the domain. We talk about the set of y values as the range. So the domain of the original function will become the range of the inverse. And the range of the original function will become the domain of the inverse. So if I have this function f, and it consists of the following three ordered pairs, 2, 3, 8, 1, and 9, 4. And let's say we want to set this up to where g is the inverse of f. So these two, we're just going to interchange x and y. So if this is x and this is y, then I just want to interchange the two and say that this first order pair will be 3, 2. The second will be 1, 8, and the third one will be 4, 9. So the domain for f, is what? It consists of 2, 8, and 9. So those values are the x values in the original function f. Now we interchanged them when we created the inverse, which is g. So now the x values became y values. So when we think about the range for g is what? It's going to be these values. So it's going to be 2, 8, and 9. And you can see that you have 2, 8, and 9 in the y location for each ordered pair, right? So that's now your range. When we think about the range for f, so the range for f, it's what? It's 3, 1, and 4. So 3, 1, and 4. So then when we think about the domain for g, it's going to be the range from f, right? So it's going to be this right here. So 3, 1, and 4. So you see you have 3, 1, and 4 in your x positions there. So just a little simple example here for you to see what we mean by inverse functions and how the x and the y values are interchanged. So first we start out with f. Again, this is a one-to-one function. You have x values of 2, 8, and 9. So nothing's duplicated there. Then you have y values of 3, 1, and 4. Nothing duplicated there. So when that occurs, for each x there's one y, and for each y there's one x, so it's 1 to 1. So then we can create this inverse, which is g, by just interchanging x and y. So we had the order pair 2, 3. We swapped everything. So this became 3, 2. So now 3 is the x value, 2 is the y value. Then we saw we went from 8, 1 to 1, 8, and from 9, 4 to 4, 9. So obviously the domain, or the set of allowable x values for f, became the range for g, because we swapped x and y values. And then the range for f became the domain for g, again, because we just swapped x and y values. So the next thing we want to talk about is the notation that's involved with an inverse function. So this is a very big source of confusion for students. So the inverse of a one-to-one function f is notated as f inverse. So that's how that's read. It's not f to the power of -1 like it appears to be. So this is a big source of confusion. If I have a function f of x and it's a one-to-one function, when I notate the inverse, I say f inverse, like that. Okay, that's what it means. So f inverse of x. So these two are inverses of each other. So these are inverses. And basically that just means these two functions will reverse each other. Now, one thing I don't want you to do, let's say you see f inverse of x. I do not want you to think that this means 1 over f of x, okay? This is a common mistake, again, because you see that -1 there, you're thinking about the rules of exponents. This is wrong. Okay, wrong. And again, I don't know who set this up, but it's really, really confusing when you look at the notation, especially if you don't have somebody there to tell you. If you just read it in a book and they don't tell you that, you might really think that this is f to the power of -1, right? It's not. So this is f inverse of x. Again, that's the inverse of f of x. All right, so f inverse consists of all ordered pairs y comma x, where x comma y are components of f. So we saw that with the simple example. We saw that every x value became a y value in the inverse. So if this is the original right here, my x value here goes into the y position. And then my y value here goes into my x position. So the x values become y values, the y values become x values. And we talked about this already. The domain of f inverse is the range of f. So in other words, the x values of the inverse came from the y values of the original. And then the range, or the y values of the inverse, is the domain of f. So the y values of the inverse came from the x values of the original function. So I know this looks a little complicated in this form, but when you break it down like that, it's super simple. X values of the original function become y values of the inverse, and y values of the original function become x values of the inverse. All right, so you might see this notation in your textbook when you first get started, and a lot of students get really confused with this one too. So I just want to take a moment and kind of break this down. I want you to see an example where you can look and understand how the functions reverse each other when they're inverses, okay? So if we see f of f inverse of x, we say this is equal to x. We also see that f inverse of f of x is equal to x. So you might say, what in the world does that notation mean? So let's look at an example, and then we'll kind of work through that, and then we'll come back in the end and we'll explain what this generic notation means. Let's say you had f of x is equal to 2x plus 3. Okay. Now, I haven't taught you yet how to determine if something is 1-to-1. We'll get to that later on in the lesson. But I just want you to believe me when I say it is a 1-to-1 function, and therefore it will have an inverse. Now, how do we find the inverse? And we'll talk more about this later, but the simplest method to do this is to replace f of x with y. So we know f of x just took the place of y when we started talking about functions. Y, or f of x, is nothing more than the dependent variable. That's all it is. So y is equal to, or y is the same as, this quantity 2x plus 3. Okay. Now all we need to do is swap x and y. So y becomes x and x becomes y. All right. So now we're going to solve for y again. So to do that, I would subtract 3 away from each side of this equation. And that would give me what? I would have x minus 3 on the left is equal to, this would cancel, so just 2y. And if I wanted to solve for y, I would divide both sides of the equation by 2, and I would have x minus 3 over 2 is equal to y, right? This would cancel with this. Let's write this over here. So you have your original function, which is y equals 2x plus 3, and then you have your inverse, which is y equals x minus 3 over 2. So these two functions are going to reverse each other. Now, the notation for this, remember, y is nothing more than f of x when we're talking about a function. And if these two are inverses, and this is the original, this is the inverse, so we notate it by saying f inverse of x. Okay, very, very simple. All right, so now we have our two inverse functions. We have f of x equals 2x plus 3, and we have f inverse of x equals x minus 3 over 2. So let me give you a little bit of insight right now into how these two functions are considered inverses of each other, or in other words, how they reverse each other. So if I start out with the original function, f of x equals 2x plus 3, I take x, whatever value I choose for that, doesn't matter what it is, I multiply it by 2 to start. So kind of step 1, I multiply by 2. Then in step 2, once that's done, I'm going to add 3. So I'm going to add 3. So as an example, let's say I choose 4 for x. So the notation for that with a function is f of 4. Just means I'm plugging in a 4 for x. So this equals 2 times 4 plus 3. 2 times 4 is 8. 8 plus 3 is 11. Okay. Let's think for a second what happens with the inverse. So f inverse of x, we first subtract away 3 from whatever x is. So step 1, we subtract away 3. Now we can see that subtracting away 3 would undo the addition of 3 that we saw in the original function. Then for step 2, we see that once this numerator is done, right, we subtracted away 3, we're going to divide by 2. So we're going to divide by 2. And that undoes the multiplication by 2 that we did in the original step of the first function. So you can see how these two would reverse each other. So if I took f inverse of 11, I would reverse the process and I should get back to 4. So this would be equal to what? So let me kind of scroll down a little bit, get some room going. This would be, plug in 11 for x, minus 3 over 2. 11 minus 3 is 8. So you'd have 8 over 2, which would give me 4. So you can see how the x value of 4 became the y value of 4 in the inverse. And the y value of 11 became the x value of 11 in the inverse. So in other words, in the original function, we have the ordered pair 4, 11, meaning I plug in a 4 for x and I get an 11 for y, or for f of x. In the inverse function, these two are interchanged. So in other words, I plug in 11 for x and I get a 4 for y. So you can see here, 11 started out as y, became x. 4 started out as x, became y. So we're just interchanging the x and the y values. Now, let me erase this, and I'll show you this generically, and then we'll kind of move on to some other topics, and we'll swing back to this. So let's scroll up a little bit, and let's see if we can make sense of this notation here. So the first thing is that we have f of f inverse of x. What does that mean when we say f inverse of x? So remember, when we think about an equation, the two sides are equal to each other, meaning they're the same as. So you might as well think of this, forget about the fact that it's an inverse for a second. We can really just say this is a function or an equation where we say we have some dependent variable, let's just call it y, is equal to x, the independent variable, minus 3 over 2. So if this right here is just asking me for what is y in the inverse? Well, y equals this guy right here. So I could plug that in right here. And I could say in the original function, so f of x minus 3 over 2 should be equal to x. Let's see if that's the case. So this is equal to 2 times, I'm plugging this in for x, so I'm plugging in an x minus 3 over 2, and then plus 3. So what happens here is that this 2 cancels with this 2, and I'd be left with what? I'd have x minus 3 plus 3, minus 3 plus 3. Those two cancel. I'm left with x, which is exactly what it tells me I would be left with. If I think about f inverse of f of x, or again, you could just think about this as y, if it's giving you a mental roadblock, this is equal to 2x plus 3, or it's the same as 2x plus 3. So I could just plug this in here. I'm saying, hey, if I have the inverse function and I plug in the y from the original function, I should get x back, right? That's what I would expect, because if I take the y from the original function and I plug it into the inverse, I know I'm going to get x. So this is f inverse of, we'll say 2x plus 3, and this should give me x back. Does that happen? Well, let's go ahead and calculate this. So let me kind of scooch this down. And let's see what this gives us. So we would plug in a 2x plus 3 there. So we would have 2x plus 3 minus 3 over 2. We know 3 minus 3 would give us 0, so this would basically be 2x over 2. The 2's would cancel, and again, I'm just left with x. So hopefully this kind of clarifies some things for you. I know a lot of students will see this notation and just really freak out and say, what does it mean? Again, it all goes to this concept where the x and the y values are just interchanged. So the x values from one function will become y values in the other, and the y values in one function will become x values in the other. All right, so let's kind of roll through some problems now, and I'm going to talk to you a little bit about how to determine if something is a one-to-one function. So first, let's look at this simple example. We have f here, and we see that we have 9, negative 2. So this is our first order pair, then 7, 1, then negative 4, 4, then 2, 5. We then see we want f inverse. So the first question would be, is this a one-to-one function? I see for my x values I have 9, 7, negative 4, and 2. So what you're looking for in a problem like this, you don't want any duplicate x values, because that would mean the same x value is linked up to more than one y value. Then you want to look for duplicate y values. So negative 2, 1, 4, and 5 don't have that. So you're looking for that to say, hey, each y value is only linked up to one x value. So this function is one-to-one, so it will have an inverse. Again, you just swap the x and y values. So negative 2 becomes the x value here, 9 becomes the y value. So on and so forth. So this would be 1, 7, 4, negative 4, and then 5, 2. So f inverse contains the ordered pairs negative 2, 9, 1, 7, 4, negative 4, and 5, 2. So the domain of f, which consists of 9, 7, negative 4, and 2, became the range of f inverse, right? 9, 7, negative 4, and 2. The range of f, which consists of negative 2, 1, 4, and 5, became the domain of f inverse, right? Negative 2, 1, 4, and 5. All right, let's take a look at g. So will g have an inverse? So the first thing is g a one-to-one function? I see I have an x value of 6, negative 12, 7, and 11. So no duplicate x values there, so we're good. So we think about duplicate y values. So you have 5, 4, 1, and then 5 again. So here, this fails the definition of a one-to-one function. So it's a function because each x is associated with only one y, but it's not a one-to-one function because each y value, in this particular case 5, is not associated with one unique x value, right? The y value of 5 is associated with or linked up to 11 and then also 6. So this fails the definition of a one-to-one function. And the reason you want something to be one-to-one, think about if I tried to make the inverse of g. So let's say I had g inverse like this, and you set it up. Well, I reverse everything. So this is 5, 6. This is 4, negative 12. This is 1, 7. And then this is 5, 11. So you say, hey, if x is 5, what's y when we think about the inverse? Well, it could be 6, but it could also be 11. So in other words, it's got to be a one-to-one correspondence to say, hey, x is 5 here, y is going to be this, right? In this case, x is 5. We don't know whether to say y is 6 or y is 11. So it's not a one-to-one function, and so it will not have an inverse. So we'll just put not a one-to-one function. All right, so let's talk a little bit about how you would go about determining if you have a one-to-one function or not. So you'll recall that when we talked about functions, we had this idea of a vertical line test. Essentially, if a vertical line hits the graph in more than one place, we do not have a function. This would tell us that the same x value corresponds to more than one y value. If we take a look at something like a linear equation, we know this is a function. I could draw as many vertical lines as I want, and I'm never going to impact the graph in more than one spot. So you see here, each vertical line would only touch the graph once. So you think about your x value, it's associated with 1 and only one y value there. So this is a function. Here's an example of something that's not a function. Clearly, this would fail the vertical line test. So if we look at all these vertical lines, you could see that for a given x value, we have more than one y value that's associated with it. So for each x, we have more than one y value associated with it. So this is not a function. So this is not a function. All right, so now let's talk about the horizontal line test. So this is similar in concept to the vertical line test, but the horizontal line test is going to tell us if we have a one-to-one function. We think about a horizontal line. A horizontal line is y equals something. So it's the same y value. If it impacts the graph in more than one location, that same y value is going to correspond to more than one x value. And so we don't have a one-to-one function. So we can say here, if any horizontal line intersects the graph of a function in no more than one spot, the function is one-to-one. Right? If it does impact the graph in more than one spot, the function is not one-to-one. So this is the graph of f of x, or you could say y, is equal to x squared minus 2. So obviously this is not a one-to-one function. So you can look at these horizontal lines and you can see that they impact the graph more than once in each case. And so this fails the definition of a one-to-one function because for the y values you're given, they have more than one x value associated with it. Now you could solve this guy for x and see why that's the case. I can add 2 to both sides of the equation. That would be y plus 2 is equal to x squared. I could take the square root of both sides. If I do that, what happens? I get plus or minus the square root of y plus 2 is equal to x. So think about that. For a given y value, I'm going to now get 2 associated x values because of this plus or minus operation. Let's pick something easy from the graph. So we know that an x value of 3 would correspond to a y value of 7. So if I plugged in a 7 for y, 7 plus 2 would be 9. I would have plus or minus the square root of 9. Square root of 9 is 3. So I'd have positive 3 or negative 3 for x. So that y value of 7 is associated with an x value of 3 and then also an x value of negative 3. So this is not one-to-one. So not one-to-one. All right, what about this function right here? Obviously, this is a one-to-one function. You can see that each line I drew would only impact the graph in one and only one spot. So for every y value here, there's only one associated x value. All right, so the next graph is one that causes a little bit of confusion. This is the graph of f of x is equal to x cubed minus 1. So I'm going to tell you right off the bat, this is a one-to-one function. So I could go through and draw horizontal lines. And you can see that all of these lines would just impact the graph once. Where students get confused or where students get tricked here, most computer software, most graphing calculators will draw this part right here looking semi-flat, right? So it kind of looks like a horizontal line would impact the graph there in more than one location. But that's not the case. If you really just think about this for a second, when x is 0, okay, when x is 0, y or f of x is negative 1. So you have the order pair 0, negative 1. That exists right there. Every value to the left of 0 for x, as we move towards negative 1, is going to decrease the y value. So this guy's going to drop this way. It doesn't drop that quickly when you look on the graph, but it does drop. So if I took something like negative 1/2 and plugged it in for x, I would get a smaller value than negative 1, right? This guy's decreasing. If I looked at the values between 0 and 1, it's the same thing. This guy is increasing here. It looks like a horizontal line right there would impact the graph more than once, but it actually wouldn't. So that's where you got to kind of look at the equation and think about, well, all right, if I plugged in something infinitesimally larger than 0, would I still get negative 1 as a result? The answer to that is no. So obviously it's not a horizontal line that would touch the graph in more than one location. So this is a one-to-one function. So this is a one-to-one function. All right, so now let's get to kind of the main thing, the thing that you're going to see most often in this section. You're going to be asked, how can you find the inverse of a function? I showed you earlier when we talked about that notation, we want to interchange x and y, solve for y, and then replace with f inverse. So I'm going to start out by just replacing f of x with y. And then I'm going to say y equals negative 10 plus 3x over 2. Now I'm going to interchange y and x. So this would be x equals negative 10 plus 3y over 2. So I just interchanged x and y. Didn't do anything fancy. Then I'm just going to solve for y. So if I do that up here, I would multiply both sides of the equation by 2. So you'd have 2x is equal to, if I multiply over here by 2, I would cancel that denominator of 2. So I would just have negative 10 plus 3y. Then I'm solving for y. So let me add 10 to both sides of the equation. So this is 2x plus 10 is equal to, that's canceled, so just 3y. The last step is to divide both sides of the equation by 3. And I would get that 2x plus 10 over 3 is equal to y. Okay, so let's erase everything real quick. And this guy y, I'm going to now replace with f inverse. Just to notate that, hey, this guy is the inverse of this guy. That's all it is. So f inverse of x is equal to 2x plus 10 over 3. So these two are inverses of each other. And again, if you wanted to think about how you could prove that to yourself, well, if I plugged in a 4 for x here, so if I had an x value of 4, you'd have 3 times 4, which is 12. 12 minus 10 would give me 2. So I'd have 2 over 2, which is 1. So on this function, we have an x value of 4, a y value of 1. Remember, the x and y's are interchanged. So if I take a y value of 1 and plug it in for x in the inverse, I should get a result of 4. So if I plugged in a 1 there, what would I get? 2 times 1 is 2. 2 plus 10 is 12. 12 divided by 3 is 4. So here the ordered pair would be what? It would be 1, 4. Again, the y value became x, the x value became y. So the values here are interchanged. All right, let's take a look at another example. So we have f of x is equal to negative 4/5 x. Again, to do this as simply as we can, y equals negative 4/5 x. We interchange x and y. So we interchange x and y. And then we solve for y. So I would just multiply both sides by 5 over negative 4. And so this would cancel with this with this. We'd have y is equal to negative 5/4 x. Or we could say f inverse of x is equal to negative 5/4 x. So if you wanted to check this, let's just choose something for x. Let's say we chose, I don't know, let's say 5. So f of 5 would be equal to negative 4 times 5 over 5. The 5's would cancel. I'd be left with negative 4. So if I take negative 4, which is the y value here, and I plug it in for x here, I should get 5 back. So if I plugged in a negative 4 here, this cancels with this, and I've got negative 1. Negative 5 times negative 1 is 5. Right? I go right back to that. All right, let's say we saw f of x equals x cubed minus 2. So again, we say y equals x cubed minus 2. And I interchange y and x. So this would be x equals y cubed minus 2. And to solve for y, I would add 2 to both sides of the equation. So that's going to give me x plus 2 is equal to y cubed. And to solve for y, I'm just going to take the cube root of each side. And so what's going to happen is I'll have y is equal to the cube root of x plus 2. Let me erase all this. We can do the proper notation. So these two are inverses, so we would say f inverse of x is equal to the cube root of x plus 2. And again, if you pick a value for x, let's say you pick 3. So 3 cubed, we know that's 3 times 3 is 9, 9 times 3 is 27. Subtract away 2, you get 25. So f of 3 is equal to 25. So I should be able to take 25 and plug it in for x and get back to 3. Right? So if I take f inverse of 25, I expect the result to be 3. So the cube root of 25 plus 2, 25 plus 2 is 27. The cube root of 27 is 3. All right, let's say we saw f of x equals the cube root of x plus 3. Again, we'll say y equals the cube root of x plus 3. Interchange x and y, so x equals the cube root of y plus 3. So let's subtract 3 away from each side of the equation. We will have x minus 3 is equal to the cube root of y. And then I would just cube each side of the equation. So I would have y is equal to the quantity x minus 3 cubed. So let's erase all this, and we'll use the proper notation. We'll say f inverse of x is equal to the quantity x minus 3, and this is cubed. All right, let's take a look at another one. So suppose we see f of x equals 3 over x minus 1 minus 2. So again, to find the inverse, we'll say y equals 3 over x minus 1 minus 2. Swap out x and y, so let's just say this is y and this is x. So how do we solve for y now? Well, we got to add 2 to both sides of the equation. So we'd have x plus 2 is equal to 3 over y minus 1. So now let's multiply both sides of the equation by the quantity y minus 1. So what would that give me? Well, this would cancel over here. I would have the quantity y minus 1 times the quantity x plus 2 is equal to 3. So let's do FOIL here. Y times x is xy. The outer y times 2 is plus 2y. The inner negative 1 times x is minus x. And the last negative 1 times 2 is minus 2. This equals 3. So let's keep everything with a y on the left, everything without a y on the right. So let's add x. Let's add 2 to both sides of the equation. So that would go away. And then let's factor out a y. So I would have y times the quantity x plus 2 there. So we would have y times the quantity x plus 2. And so what we would do here is just divide both sides of the equation by x plus 2. And that's going to give us what? Y is equal to, you would have, we'll reorder this to x plus 5, right? Because we have x plus 3 plus 2. 3 plus 2 is 5, over x plus 2. And again, to notate this properly, we'll say f inverse of x is equal to x plus 5 over x plus 2. And again, you can choose a value for x, plug it in the original function, you'll get a y. Take that y value, plug it in for x in the inverse, and you'll get your original x value back. So as an easy example, let's say x was 4. So f of 4 would be what? Plug in a 4 there. 4 minus 1 is 3. 3 over 3 is 1. So you'd have 1 minus 2, which is negative 1. So if I plugged in a negative 1 for x in this inverse, negative 1 plus 5 is 4. Right? So this would be 4 over. Negative 1 plus 2 is 1. 4 over 1 is 4, so I'm right back to 4.